This video covers the solutions in class activities, and we're going to start off by looking at part A. The first question, which of the following compounds will be the most soluble in pentane? So as we look at this question, we need to look at like dissolves like. So we are looking for similar intermolecular forces. Now, so we examine the intermolecular forces for pentane. It only has London dispersion forces. So it only has those carbon-hydrogen bonds, and those are non-polar bonds. So we only have London dispersions. And so that's the strongest intermolecular force within that hydrocarbon. Now let's look at the ethyl methyl ketone. As I draw the Lewis dot structure for it. So you have the carbon oxygen bond here. So you have a dipole right here. So we have dipole-dipole forces. So that's the strongest intermolecular force here. But remember, all things do have London dispersion forces. So it does have London dispersion forces, but the dipole-dipole interaction is going to be the strongest. So that's the one that we're most concerned with. Then as we look at pentanol, notice we have that OH at the end. And when that OH is attached to a carbon, that's an alcohol. Now, if the OH is attached to a metal, that's a hydroxide and that's a base. But if it's an OH attached to a carbon, that's an alcohol. And so when we think alcohol and that OH, we should be thinking hydrogen bonding forces. So remember hydrogen bonding, this is a stronger type of dipole-dipole. And as we look at the types of hydrogen bonding, you're looking for either an OH bond, an FH bond, or an NH bond. So think of spelling phone funny. So FH, OH, or NH gives you hydrogen bonding. So these are all both too strong for just the pentane. Then as we look at the acetic acid also has a dipole, but it also has a hydrogen bonding. So this is a carboxylic group. So we have a COOH attached to a carbon. So when you have that, this is what we call a carboxylic acid. So when you have this COOH attached to another carbon, it can be a longer chain carbon or a smaller chain like this. But when you have this group, it is a weak acid. So you have the dipole-dipole here, and you have the hydrogen bonding possibilities here. So hydrogen bonding is the strongest type of intermolecular force there. Now, if we look at the benzene, benzene only has carbon and hydrogen in it, and this is the structure. It's a ring with alternating double bonds, double and single bonds. So if we only have carbon-hydrogen bonds, those are non-polar bonds. The strongest type of intermolecular force we're going to have is only those London dispersion forces. So this is why the benzene and the pentane should be soluble, because they both have like type intermolecular forces. They both have London dispersion forces as their strongest intermolecular force. Now here we're looking for the situation that would result in an exothermic delta H of solution. So this is to form a solution from the solvent and the solute coming together to make that solution an exothermic exit. So the heat is coming out, so our products are going to be lower in energy. So to help you visualize this, we're going to start off with reactants at some arbitrary value. And if we want it to be exothermic, it's going to be lower in energy because that's heat had to come out of it. So heat or that energy had to come out of the system. So as it went to lower energy, energy was released. And so that's the delta H of solution, that difference in energy there. And because the products is lower than the reactants, this is exothermic. So we've got an exothermic setup, but this is looking at going from the solvent and the solute going to make the delta H of solution. So the first thing we're going to do is break up the solute-solute interaction. And remember, breaking a bond and breaking an intermolecular force always requires energy. So we're going to put energy in, and we're going to break up the solute and solute interactions. So that's the delta H of the solute. Now we're going to look at what is the delta H of hydration. So the delta H of hydration is the breaking of the solvent-solvent interactions, but also the solvent and solute coming together. So they've combined two things here. It's the breaking of the solvent-solvent interactions and the solvent and the solute coming together. Because remember, to make that solution, we had to have three things happening. We had to break up the solute-solute. We had to break up the solvent-solvent. Those all require energy, so you go up. But as you form the solvent and the solute interaction, that's favorable, so energy is released, so it comes back down. But the delta H of hydration combines the solvent-solvent interactions and the solvent-solute interactions. So if I need to have an overall exothermic reaction, the delta H of hydration has to be larger than the delta H of reactants. Because also to remember, so that delta H of the solute plus the delta H of hydration gives you the overall that delta H of solution. So if the delta H is larger, remember the alligator eats the larger thing. So the delta H is larger than the delta H of solute for this exothermic. Now, if it was endothermic or greatly endothermic, this would be a smaller value and the products would be higher in energy than the reactants. So let's go on to number 3. So which of the following ions should have the least exothermic hydration? So remember, we said the delta H of hydration is the breaking of the solvent-solvent interaction, so that requires energy. And then the solvent and solute coming together, so that's favorable, so that releases energy. So we're looking for the least exothermic, so it falls the lowest amount. So this is where Coulomb's law that we discussed in Chem 1A comes into play. But basically, it's relating the attraction of those ions to each other in relation to its radius. So the higher the charge, so this is what the Q's represents. So the magnitude of the charge, so +1 or +2 or -2 or -3, whatever they may be. So those are the charges. And then R is the radius. So typically the size of the charge makes a bigger impact on this value than does the radius squared. So as we look at these options here, we notice that we have an aluminum 3+, and then magnesium 2+, calcium 2+, and then the strontium 2+, but also the sodium plus. So the extremes here will be the sodium plus and the aluminum 3+. So the aluminum 3+, this is a large charge. So we would expect it to be greatly attracted to the polar water. It's a bigger charge, it's hungry for those electrons. So you're gonna have a strong interaction. So a strong solvent-solute interaction, so it drops very low. But we want the least exothermic, so we need the smallest attraction to the water. So we would expect the smallest charge to have the weakest interaction. So again, looking at Coulomb's law, the smaller the ion, so the smaller this radius here and the greater the charge here, the bigger this number is, the stronger the interaction, so that force right here. So stronger interactions, more favorable. More favorable means more negative. So the more negative, the more exothermic it is. But we want the least exothermic. So in this case, this would be the sodium. So it's the smallest, and it's got this smallest charge, magnitude of the charge for these. So this is why the force would be the least. Now in question 4, we're looking at the relationship between temperature and pressure on solubility. So if we look at the effect of temperature on the solubility of gas, so we have to think about what's happening to the molecules at lower versus higher temperatures. So remember, at lower temperatures, the molecules are moving much slower. Higher temperatures, things are moving much faster. So think about a fish. If you've ever had a fish tank and it got too warm, you think about what happened to the fish. You might have accidentally killed your fish because not only is the water too warm, but if it's warm, it can't hold as much dissolved oxygen, and they need that dissolved oxygen to breathe. So there's an inverse relationship to the temperature and the solubility of a gas, because at higher temperatures, those molecules are moving around really, really, really fast, and they're going to hit those oxygen molecules, and those oxygen molecules are not going to be able to stay dissolved in solution. They're going to leave. But if the molecules are moving slower, even when they run into the oxygen molecules, then they're less likely to knock that oxygen out of the solution. So colder solvent, molecules are moving slower. They're less able to push the dissolved gas out of the mixture. So definitely temperature affects the solubility, but also the pressure. So think about what's happening to the solute molecules at lower versus higher pressure. So some applications that you can think of to help you rationalize this out are thinking about your carbonated drinks, such as my favorite, Diet Dr. Pepper. So when they bottle or they can the carbonated soda, they pressurize it. They pressurize it so the gas on top of the liquid has a lot of pressure. They're close together. There's lots of molecules in it. They don't have much space in the gas. They're moving around really quickly. So they are going to move more of them into the solution because there's just too much pressure here. But when you release the pressure, when you open up the can, you hear this whoosh as the gas escapes. And so eventually, if you leave it open long enough, your Coke will go flat. And it's flat because you have less dissolved CO2 in there. So the higher the pressure, the molecules are closer together, they're crowded, and they're pushing harder against each other. So they're better able to push into the solvent to get away from the other pushy gas molecules. So a visualization here. So here we're increasing the pressure by decreasing the volume. So notice how more of these red particles move into the solution when you increase the pressure. So both the solubility, the solubility of a gas is both dependent on the temperature and the pressure. So for my anglers, they're my fishers and also my biology majors. So this is why if you go fishing for trout, especially lake trout, you need to go down deep where it's colder because the trout need good oxygen-rich environment because they're very sensitive to temperature and the oxygen environment because they'll easily die. So if you're going to be fishing for them, you're going to need to fish them in the colder, deeper parts of the lake. That's where you're going to find them. They're not going to be at the surface level where it's warmer, where there's less dissolved oxygen in the lake. Now in question 5, we're going back to this idea of the delta H solution and looking at going from reactants where we have our solute and our solvent and going to products. This one, we're doing a calculation. They want us to determine the delta H of solute. So remember, this is this energy required to break up the solute intermolecular forces. So they tell you that the delta H of solution is 19.9 and the delta H of hydration is negative 670. So the delta H of hydration here is negative 670. And then the delta H of solution is positive 19.9. So if I were to change this diagram, since it's a positive value, this product would actually be higher in energy, but I didn't draw it that way. I just kept it as exothermic from when I cut and pasted it from the previous problem. But in this case, since that delta H of solution is positive, it's endothermic, so this product would be higher in energy. Okay, but anyway, the solution, the delta H of solution is a combination of the delta H of solute plus the delta H of hydration. So we're going to plug in our values and solve for the delta H of the solute. So I'm just going to combine my plus and my negative here to minus, and then move my negative to the other side. So I'm going to add 670 to both sides to get my delta H of solute. So the delta H of solute is 690 kilojoules per mole. And then for question 6, which of the following should have the largest Henry's law constant in water? So this is Henry's law. So this is the constant. So this is some proportionality, and this is the pressure of the gas. And so this is how soluble the gas is inside the solvent. So we're looking for the KH in water. So if it's going to be a large KH, that means it's going to be more soluble. And remember, we said like dissolves like. So the more soluble a solute is in the gas, the bigger the KH is. And the bigger that KH value is, the more soluble it is. That means they're also going to have more similar intermolecular forces. So if we increase the KH, the solubility to increase, and to increase the solubility, you're going to have more similar intermolecular forces. So that's what we're going to analyze. So KH, so if we're looking for the water, water has hydrogen bonding forces. So we're looking for one of these options that also have hydrogen bonding forces or the closest to that. And as we analyze the intermolecular forces for these problems, the ethane only has London dispersion because you only have carbon hydrogen. These are non-polar bonds. Argon is just the atom themselves, so they only have London dispersion forces as those argons interact with other argons. The NH3, remember spelling phone funny because you have NH bond, so you've got hydrogen bonding. So hydrogen bonding and hydrogen bonding here, but I'm going to analyze everything else just to make sure there's not a better answer. And then the xenon, it's only one atom, so you only have London dispersion forces. And then the CO2, you have dipole because you have a polar carbon oxygen bond. So the one that has the most similar type of intermolecular forces would be the NH3 and the water. They both have hydrogen bonding possibilities. So just to show you, I looked up the values for the Henry's law constant in water for these things. I put them in order of the increasing KH. So here we're going increasing solubility if we're all at the same pressure. So notice that argon has the least. This is the smallest molecule, it's a sphere. Xenon is larger. So the point of contact, the surface area as they come into contact is greater for the larger xenon. So we see a slightly larger KH. And then the CO2, that dipole interaction, so even larger. So we go from 10 to the minus 5th to 10 to the minus 4th. So that's a magnitude of 10 difference. But here we've got a magnitude difference of 10 to the 3rd. So that's a big difference as we go from the CO2, which has dipole-dipole, but a net dipole of 0. So, but we have hydrogen bonding in the NH3 that's very strong. It's a polar molecule. So this is why this has the larger KH value. And then last problem in part A for solutions, the Henry's law constant for helium gas, they give it to us at this temperature. So we have the KH value and they have the partial pressure of the helium at 0.55 atmospheres, and they want to know the concentration of that helium in the water. So I'm using my Henry's law equation. I'm going to plug in my KH value. I plugged in my pressure because I'm looking for the solubility of the gas. So when I do the math here, so the molarity per atmospheres times atmospheres cancels out. I'm in units of molarity, and that makes sense with the solubility of the gas. Those units make sense. So this is how I got the value of 2.04 times 10 to the minus 4th molarity. So answer D for number 7. So remember, if you have questions, please don't hesitate to ask me in class or come to office hours, but I will see you later, and I will post the answers to study guide for in-class activity part B.